All right, today we're going to do something pretty ambitious. We're going to build a brain. Well, not a real squishy one, but an artificial one. We'll start with just the most basic pieces and see how we can put them together so that a machine can actually learn. Let's dive in.
So let's kick things off with a huge question. I mean, our brains are unbelievably complex, right? But what if we could capture the magic of learning using a bunch of really simple rules? This is the very idea that launched the entire world of artificial intelligence that we see all around us today.
And it all starts with this, the artificial neuron. Think of it like a tiny little gatekeeper or a decision maker. It takes in a bunch of different signals or inputs. Now, not all inputs are created equal. Each one has a different level of importance, which we call a synaptic weight. The neuron just adds them all up, and if that total number crosses a certain line, a threshold, it fires. It sends its own signal out. And this isn't just a simple on-off switch. It uses what's called a nonlinear activation function, which just means it can have a more nuanced response.
Okay, so why even bother doing all this? What's the big deal? Well, for one, these networks are what we call massively parallel. Thousands, even millions of these little neurons can all be working at the exact same time, which makes them incredibly fast. This structure also just happens to be a perfect fit for our modern computer chips. Plus, they're universal information processors, meaning the same basic setup can tackle all sorts of different problems. But the real magic, the thing that changes everything, is that they can learn from their environment and adapt.
So how do they learn? Well, there are two main styles. First up is supervised learning. This is basically like studying for a test with an answer key. You show the network an input, maybe a picture of a dog, and you tell it the correct answer is dog. The network makes a guess. If it gets it wrong, you use that error to tweak all its little internal weights, making it just a tiny bit more likely to get it right the next time. Then there's unsupervised learning. Here, there's no answer key. You just dump a whole lot of data on the network, and it has to figure out the patterns and structures all by itself.
The theory behind all this comes down to one absolutely critical goal: generalization. You see, it's a huge balancing act. How can a machine learn from a handful of examples, but then make accurate predictions about brand new stuff it has never ever seen before? The whole point is to build a model that understands the deep down patterns in the data without just memorizing the specific examples you showed it.
Okay, let's start with the most basic neural network you can build, the perceptron. It's really just a single layer of those artificial neurons we talked about. It takes in some inputs, and based on its weights, it spits out a decision. It's kind of the hello world of neural networks.
And the way it learns is just beautifully simple. First, you just set all its weights to random little numbers. Then you showed an example from your data. You see what it guesses. If it's wrong, you just nudge the weights a little bit in whatever direction would have made that error smaller. And you just keep doing that over and over again for every single example. And slowly but surely, the network gets better. It's a classic case of learning by correcting your mistakes.
And here's something amazing. A theorem actually proved that for certain kinds of problems, this super simple learning rule is guaranteed to eventually find a solution. The network will converge. It will find the right answer. But, and this is a huge but, there's a key phrase in there: for a certain class of problems. That implies that some problems it just can't solve. Let's look at one of those right now. So let's put our simple little brain to the test with a classic logic puzzle. It's called the XOR problem, which stands for exclusive OR. It sounds really simple on the surface, but it's going to reveal a critical, fatal flaw in our current design.
The rule is dead simple. The output should be 1 if and only if the two inputs are different. So if one input is on and the other is off, the output is on. But if both are off or both are on, the output is off. Seems straightforward enough for our network to learn, right?
Well, here is the catch. A single-layer perceptron is what's known as a linear separator. Imagine plotting those 4 input possibilities on a simple graph. All the perceptron can do is draw one single straight line to try and separate the 0 outputs from the 1 outputs. And if you try to do that with the XOR puzzle, you just can't. It's impossible. The problem isn't linear. Our simple brain has hit a wall. It is completely stumped.
So how do we get past this wall? The solution is surprisingly elegant. You just add more layers. By sandwiching new layers of neurons between the input and the output, we create something way more powerful: a multi-layer perception, or an MLP. These hidden layers are the secret sauce. You see, they're not directly connected to the outside world. Instead, they act like internal feature detectors. The first hidden layer might learn to recognize really simple things like little diagonal lines or curves.
The next layer can then take those patterns and combine them to recognize more complex shapes, like an eye or a nose. It's this ability to build up ideas layer by layer that lets the network move beyond a single straight line and create the complex boundaries it needs for harder problems.
But this creates a new challenge, right? How do you train those neurons in the middle? You can't directly measure their error because you don't have a correct answer for them. The solution is a brilliant algorithm called backpropagation. What it does is it calculates the total error at the very end, at the output, and then it works backwards, layer by layer, sharing a little piece of the blame with every single weight in the entire network. This is how every single weight gets adjusted just right.
Now, when we train these bigger networks, we usually have two modes. In sequential mode, we update the weights after every single example. It's like getting immediate feedback. In batch mode, we go through the entire training set, figure out all the changes we want to make, and then apply the average of all those changes at the very end. This gives us a much more stable and steady learning path.
So let's recap. We've upgraded our brain. We gave it depth by adding these hidden layers, and we gave it a really sophisticated way to learn with backpropagation. Now, with these two new powers combined,
That XOR problem, the one that was totally impossible for our simple little perceptron, it's a piece of cake. The multi-layer perceptron can easily learn the curvy, nonlinear boundary it needs to solve the puzzle. And that right there is the perfect illustration of the incredible leap in power you get just by adding depth.
So think about that. We just saw that adding even one hidden layer was enough to solve a puzzle that was literally impossible before. That exact same principle is what's driving all of modern AI. It really makes you wonder, if that's what one extra layer can do, what kind of impossible puzzles are we going to unlock with networks that have hundreds or maybe even thousands of layers?